be talking about limits. We're not just talking about any regular limits and just limits in general. We are going to be talking about evaluating limits numerically by putting in numbers and getting an answer. So, finding limits numerically is one of the three main ways to find limits. The other two ways are uh, evaluating limits graphically and uh, analytically. Now those ones will be featured in a later video, but right now we're going to be talking about evaluating limits numerically. So, in this first example that we have the limit of as x approaches 4 of x minus 4 over x squared minus 3x minus 4. So if you were to just plug in 4 by itself, you would get the indeterminate form of 0 over 0. That is the only indeterminate form other than infinity over infinity, which will be gone over in a different video. So for right now, 0 over 0 is our only indeterminate form. So going back to this problem, we have the limit as x approaches 4 of x minus 4 over x squared minus 3x minus 4. So, like I said, this is an indeterminate form, so we will have to plug in certain numbers very, very close to 4 to see what the actual limit is going to be. So, I've already created a table of numbers that are going very, very close to 4, but not 4. As you can see, I have 4 as a question mark because we don't know what the limit of 4 actually is. So, what we need to do is plug in, let's plug in 3.9 into the equation. I've already done this, so that comes out to become 0.2041. You guys can pause this video and work on this yourself to see if you get the same answers that I do. But continuing on, so if we were to plug in 3.99 into the equation, the calculator gives us 0.2004, and 3.99 being put into the equation, it gives us 0.200. Now, if we were to go on the opposite side and put in 4.001, a number that's close to 4 but on the more positive side, we get 0.200, like we did with 3.999. Now, 4.01 actually gives us 0.1996. Running out of room there, but I was able to get it. And now 4.1 actually, when putting that into the equation, it gives us a smaller number of 0.1961. 0.1961. So, as you can see, when it gets very, very close to 4, both the right side and the left side, you're able to see that right here at 3.999 and 4.001, it goes to 0.2. So, the limit, so we can pretty much conclude, if we were to put, so let's rewind here. So, if we were been given another, if we were given another number like 3.9999 and 4.0001, that would have most likely have given us 0.2000 again. So we can pretty much conclude that the limit as x approaches 4 of x minus 4 over x squared minus 3x minus 4 is 0.200. So that limit is equal to 2.00. So if we wanted to include that in a, put that as a fraction, that is 1/5. Some teachers or professors will say whether you must put it into fraction form or decimal form. So, but if you know the transition from decimal to fraction and from fraction to decimal, then you'll be able to choose whether you want to do either. So, let's go on to another problem. One where we don't really need to do a chart. So, we have a very special one. This one is the limit, let's scroll up a little bit more, as x approaches 0 of sine of 2x over x. So what is that? You would assume that, let's just put it in numerically and say, oh, that's 0 over 0, that's an indeterminate form. But wait, that if you learned about that in class, you would realize that is theorem 1.9, and that is actually one of the two famous trigonometric limits. And with that, the original statement is limit as x approaches 0 of sine of x over x. And that is equal to 1. So a theorem 1.9 states that the limit as x approaches 0 of sine of x over x is 1. So that's theorem 1.9. So let's go back to our original problem of the limit as x approaches 0 of sine of 2x over x. So any number, let's say that like we have 2x in the sine, we can pretty much assume that since we have sine of x over x in theorem 1.9 is equal to 1, the limit of it is, we can, any number in that sine of 2x, we can multiply by the 1 here. So the 2 can be multiplied by this 1 here, and that limit will be equal to whatever number you're multiplying by 1. So the limit as x approaches 0 of sine of 2x over x is, in fact, 2. I am looking in the back of the book, and that is that number. Yes, so you can do it either the way that I explained to you, or you can do it the other way by using the table and the plotting points close to 0, and finding out that the limit is 2. So let's go to another problem here. Let's go up a little bit more. So we have the limit as x approaches 1 of x minus 2 over x squared plus x minus 6. So we have this equation here. We have the limit of the equation. From the looks of it, you can actually plug and chug. So if so, we can easily just plug it into a calculator. So 1 minus 2 is negative 1. So it's going to be negative 1 over, so we have 1 squared, that's 1, plus another 1, that's 2. 2 minus 6 is a negative 4. So we want to simplify that out, and that comes out to being positive 1 over positive 4, because a negative over a negative is a positive. and that also comes out to 0.25. So the limit as x approaches 1 of x minus 2 over x squared plus x minus 6 is 1/4 or 0.25. So let's go on to another problem. Let's go to one that has slightly bigger numbers. So we have the limit as x approaches -4 of x plus 4 over x squared plus 9x plus 20. So let's just plug in the numbers. It's normal, just doing the normal plug and chug. We have -4 plus 4, and that's going to be 0. And then let's see. Okay, so we have -4 squared on the bottom. We're doing the one on the bottom. So we have -4 squared. So that's -4 times -4. That's 16. And then you have 9 times -4. 9 times -4 is -36. So you have 16 minus 36 plus 20. So what does that equal? So it's 0 over, so 16 minus 36. That comes out to being -20. Then you add 20, that becomes 0. So we have the over so happy indeterminate form. So what do we need to do? We need to create a chart or a table to actually find out what the limit comes out to be. So what numbers can we use? Oh, let's just use the ones that are very close to -4. So we use, let's create our table. So we have x on the top and f of x on the bottom. And then we use -4.1 and then -4.01 and -4.1. And then we have -4. We're going to put a question mark under it. And then we have -3.999, -3.99, and -3.9. So let's put in to our calculator what negative of the actual numbers are. So what I want you guys to do is I want you to pause this video and do this one for yourself. And when you actually unpause the video, we're going to go over what the answers are for these charts. So here we go. Alright, welcome back, guys. So what are we going to do to actually plug in the numbers? So we need to plug in for every x that we see on the table into the actual equation x plus 4 over x squared plus 9x plus 20. So we need to do -4.1 plus 4, and that comes out to -0.1. Divide that by -4.1 squared. Hold on here. -4.1 squared plus 9 times -4.1 plus 20. That comes out to be 1.11. And then you need to do the same again. So -4.01. Actually, hold on. I messed up on this one. This is supposed to be -4.001. Sorry, my bad. So you need to do -4.1 plus 4. That comes out to -0.01. Then you need to divide that by a -4.01 squared. Then you need to do plus 9 times -4.01. And then add that by 20. And that should get you 1.01. And then you need to do once more on the -4 side, on the more negative side. So you need to do -4.001 plus 4. And that gives you, I'm getting it into scientific notation, but it's negative 0.001. And then you divide that by uh, negative 4.001 squared. And then you add that to 9 times negative 4.001, and then you add 20 to it. So it comes out to 1.00. Then you need to do it on the opposite side. And we can pretty much assume that this is going to be 0.100. So let's just go ahead and do it. So negative 3.99 plus 4, that comes out to 0.01. And then you divide that by negative 3.99 squared plus 9 times 3, negative 3.99, or 999, I should say. Alright, let's go back and let's do negative 3.999 plus 4. That comes out to 0.001. And then you divide that by negative 3.999 squared plus 9 times negative 3.999 plus 20. And when you actually get it, it's actually, my bad, it's 0.999. But when you round it up, it's going to be 1.000. Right? So now you do negative 3.99 plus 4. Then you do the same thing. So it's negative 3.99 plus 4, that's going to be 0.01. Then you divide it by negative 3.99 squared plus 9 times negative 3.99 plus 20. That comes out to negative, or positive 0.99. And then you do it once more, negative 3.9 plus 4, that comes out to 0.1, and you divide that by negative 3.9 squared plus 9 times negative 3.9 plus 20, that comes out to 0.909. So with this, the limit as x approaches negative 4 of x plus 4 over x squared plus 9x plus 20 is going to be 1. Because, like I said, those two are the same, even though that's 0.999. You can round that up to becoming 1. So, let's maybe try just one more problem in this. Let's see if we can find something that is very, very simple. Let's see, so we have, let me go back to the right section in our textbook here. So, we need to, we're going to do, for our last one, we are going to be doing a piecewise function again. So it's going to be f of x. Oh, come on. So we have f of x is equal to this piecewise function of x squared as x is less than or equal to 2. Then we have 8 minus 2x. Don't know why that's doing that. 8 minus 2x as 2 is less than x, which is less than 4. Then we have 4, in which x is greater than or equal to 4. So how do we do that one? Well, we need to do just by looking at it, we need to actually graph it in order to actually find it out. So we have our, this is actually going to be part of the graphing limits, evaluating limits graphically. So we have, let's just do 2, 4, 6, and we have 1, 2, 3, negative 3, negative 2, negative 1, and 1, 2, 3. So we have, that's just looking at x squared. So x squared is valid as long as x is less than or equal to 2. So we need to do 2 right here. Actually, hold on. 2 squared is going to be 4. And then we need to just pretty much create the parabola for x squared. So that's going to be f of x equals x squared. And then we need to do 8 minus 2x, which will go down to actually 4. So let's extend this real quick. Doing a lot of messes tonight, so bringing that out. So that goes to 4. Now this goes to there, but there's going to be an open circle because, as you can see here, as you can see in the less than signs, they're not equal to each other. So it's not less than or equals, but we're just looking at that one right there. We need to find out why. We needed to find out why that's an open circle. It's because x is less than 4. It's not less than or equal to 4. So our next one is 4 is as long as x is greater than or equal to 4. So we come up here, and then so this is our actual f of x equals 4. And with that, this is going to be a closed circle because you have x is less than or equal to 4. And this is our f of x equals 8 minus 2x. So this may be a little bit more confusing, but if you actually understand the concept of doing it graphically like this, you'll be able to actually solve more problems using the using graphing utilities to find the limits. So for the actual limit of this, it's actually going to be limit as x approaches 4 of f of x is 4. Because you have a hole here, and then it starts at another point there. Actually, never mind. My mistake. There is actually no limit because the right-hand limit does not equal the left-hand limit. So the right-hand limit does not equal the left-hand limit. So, like I said, this may be a little bit more confusing, but we'll be going more in depth with this in an upcoming video where we evaluate limits graphically. So, this was a video on evaluating limits numerically with example of finding a limit graphically. If you have any questions or have any comments or anything, let me know in the comments below, and I might just reply to you and or make another video on a question that you may have. I'll see you next time, guys.